Now, based on a few things that we learned in the previous two sessions, let's quickly recap our understanding of rational and irrational numbers, things that have been taken care of in the past, but a quick breezy recapitulation of rational and irrational numbers. Now, realistically, the entire set of real numbers could be classified as follows. There are numbers in which could be, let's say, expressed in the form P by Q, where P and Q are integers, Q is not zero, and P and Q are coprime. They can be expressed in this form. I mean, say a number of the form 2 by 7. 2 and 7 are integers, denominator is not zero, and it can be expressed in the ratio of two integers where these integers are relatively prime, have no common factors. However, if you look at 4 by 14, does this belong to the same category? Yes, because this could be eventually expressed in the form P by Q, where P and Q are integers and P and Q are coprime with the denominator not being zero. So 4 by 14 and 2 by 7 essentially belong to the same category, because 4 by 14 could be reduced to this format where P and Q are integers, Q not zero, P and Q are coprime. Such numbers are referred to as rational numbers. Now, when it comes to rational numbers, there are two categories. Say numbers of the form, say for example, let me give you an example, 0.815. Okay, now what's special about this number? This number is like 815 divided by 1000, which is 163 divided by 200, right? That's one kind. The other kind is, say, a number of the kind 0.81111111, non-terminating but recurring. This is a decimal representation. In which there is, it terminates. This is a decimal representation in which it does not terminate but recurs, right? Now, this, of course, if it terminates, we clearly understand it could be written in the form P by Q, where P and Q are eventually coprime, right? It could be written as a ratio of two integers, and if the two integers have a common factor, that could be cancelled, and eventually the last lap would be to write it in the form that numerator and denominator have no common factors. Now, something like this, can this be written? This is a decimal representation in which it does not terminate. The decimal representation does not terminate. It goes on till infinity, but it recurs. It's non-terminating but recurring. It's non-terminating but recurring. Non-terminating, it does not terminate, the decimal does not terminate, and but it recurs, recurring. Now, how do I know whether this is going to be a rational number? How do I know if I could write it in the form P by Q, where P and Q have no common factors? Can I do that? Yes. If it's non-terminating but recurring, I could represent it in the form P by Q, where these conditions are enjoyed. How do I do it? Say, let me write this as x equal to 0.81111 up to infinity. Yes or no? Right? When I do that, then 100x, see, if I multiply by 100, I get 81.11111. etc. Right? Now, if I subtract, or one more thing, I write 10x. 10x. See, if x is this, what is 10x? 10x would be 8.111111. That would be 10x. 100x would be this, 10x would be this. Now, after the decimal, the recurring portion should occur. After the decimal, the portion which is recurring, see, 11111, which is recurring, is occurring after the decimal. Such is the manipulation that I have carried out in writing 100x and 10x. Now, if I subtract 100x minus 10x, then the recurring portion will get cancelled. The recurring portion will go into oblivion. So I get 90x. On subtracting, I get 90x equal to 81 minus 8, which is 73. Because the decimal portion will get cancelled. So 90x is 73, which is like 100x minus 10x. 90x is 81.1111 minus 8.1111. That's 73. So that gives me x equal to 73 by 90. So a decimal portion which recurs, which recurs but does not terminate, recurring non-terminating. This is decimal representation which terminates, does not recur. This is decimal representation which keeps recurring, non-terminating or recurring. Now, if that happens, non-terminating and recurring, then you could see very easily that it could be written in the form p by q, where p and q are integers, and eventually there is no common factor between the numerator and denominator, causing this to be a rational number. Yes or no? So rational numbers, which are essentially ratios of two integers, and the common factor having been cancelled from the numerator and denominator, would leave the rational number in the form that numerator and denominator have no common factor between them, and causing the numerator and denominator to be rendered co-prime. If two numbers are co-prime, what is their HCF? If two numbers p and q are co-prime, what is their HCF? If they are co-prime, means they have no common factor other than 1. And if they have no common factor other than 1, their HCF must be 1. So if p and q are co-prime, the HCF of p and q would be 1. Just a passing remark. So then, this is the two broad categories of rational numbers. These are the two broad categories of rational numbers. Those that terminate, those that do not terminate but recur. Those that do not terminate but recur. It keeps recurring and does not terminate. And the same recurrence occurs. Now, what is the difference between these two? Let us try and understand. So this is non-terminating but recurring kind of a rational number. This is a terminating rational number. This is a terminating rational number. What's the difference between a terminating rational number but non-terminating but recurring kind of a rational number? Let's examine the difference between these two, right? Okay. Now, one was 0.815, like I said. One was like 0.815, which I wrote as 163 divided by 200, which was a rational number, that was terminating. The other one was 0.81111, which was a non-terminating but recurring kind of a decimal. Non-terminating but a recurring kind of a decimal. This also I could write as ratio of two integers, 73 divided by 90. 73 divided by 90. Now what's the difference between these two? That needs to be understood. So this I said is terminating. This is non-terminating and recurring. Non-terminating and recurring. Now the difference between between these two, eventually when both are expressed in the form P by Q, where P and Q are co-prime, see, I have left the two in the form P by Q. Both have been reduced. Both have been reduced to the form P by Q, ratio of two integers, where Q is not 0 and P and Q are co-prime. Both have been reduced to a form, both this and this are already in the form P by Q, where P and Q are co-prime. If P and Q are co-prime, what is their HCF? Their HCF is 1, right? Now, having expressed both in the form P by Q, where P and Q are co-prime, realize the denominator of this is what? 200. That's the denominator of this. Let me express this as a product of powers of primes. Now, this could be written as 2 into 100, which is like 2 into 10 squared, which is 2 squared into 5 squared, which is like 2 cubed into 5 squared. Yes or no? The denominator is of the form 2 to the power n into 5 to the power m. Yes or no? It's of the form. The form of the denominator is 2 to the power m into 5 to the power n, where m and n are non-negative integers. M and n are non-negative integers. Yes or no? Right? That means the denominator of this, after having been reduced to a ratio of co-prime integers, the denominator of this is such that it has factors that are only 2 and 5. It has factors that would be either 2 or 5 or both. Yes or no? It has no other factor other than 2 or 5. It has no other factor other than 2 or 5. Now, no other prime factor. What I mean is, the only prime factors of this could be 2 or 5. Whereas, look at this 90. This 90 is actually 9 into 2 into 5. Yes or no? Which is like 2 into 3 squared into 5. 2 into 3 squared into 5. Hey, now this one, in addition to having prime factors 2 and 5, it also has a prime factor 3. It also has a prime factor 3. In addition to having prime factors 2 and 5, it has a prime factor 3. So then the rule of the game, write down. If a rational number is such that it is expressed in the form P by Q, where P and Q are co-prime. If a rational number is such that it's expressed in the form P by Q, where P and Q are co-prime, in a manner that the denominator has no other prime factors other than 2 or 5, has no other prime factors other than 2 or 5, it will be terminating kind of a rational number. It will be a terminating kind of a rational number. 163 by 200 is already in the form P by Q, where P and Q are co-prime, and the denominator has prime factors nothing except 2 or 5. 2 or 5. No other prime factor as factors except 2 or 5. Whereas in this case, this is also a rational number and a non-terminating recurring kind of a rational number. In this case, look at the denominator. Look at the denominator. The denominator has prime factors 2, 5. In addition, it has a prime factor other than 2 or 5. Other than 2 or 5. So it has a prime factor 3. Do you realize that? Every time you encounter in the denominator a prime factor other than 2, then you can claim that it has to be a non-terminating kind of a rational number. Non-terminating recurring kind of a rational number. Yes or no? Right? So, just to formally put matters, a number of the form p divided by 2 to the power m into 5 to the power n, where the numerator and denominator have no factors in common. It's a rational number that will always be terminating. This will always be terminating, where m and n are non-negative integers. When I say non-negative, that means m and n could be 0. M and n could be 0. That's allowed. Whereas if I have p divided by, say, 2 to the power m into 5 to the power n, where m and n could be 0 or non-zero. In addition, there is a prime factor p1 to power alpha 1. In addition, there is a prime factor p1, where p1 is neither 2 nor 5. p1 is neither 2 nor 5. If this happens, and if there is nothing common between the numerator and denominator, the numerator and denominator are co-prime, have no factors in common, then this kind of a rational number would be a non-terminating recurring kind of a recurring kind of a representation of rational numbers. Yes or no? Right? Essentially, you know, it's not a difficult proposition to examine. Say I have 11 divided by 2 cubed into 5 squared, say. Right? First of all, examine that there are no common factors between 11 and the denominator. There aren't. Then perform the next step. Realize that in this case, the power of 5 is 2, the power of 2 is 3. If I multiply numerator denominator with 5, then this will become like a 55 divided by 2 cubed into 5 cubed. Yes or no? Which is like 55 divided by 10 whole cube. Yes or no? Which is like 0.055, which is a terminating decimal, kind of a rational number. So eventually, if there is nothing common between the numerator and denominator, I repeat, and the denominator is of the form 2 to the power m into 5 to the power n, where m and n are non-negative integers, then the rational number must be of the kind terminating decimal. Whereas if you had, say, 11 divided by 2 cubed into 5 squared, and say there was a 3 also associated with it, this time it will not be terminating. Realize that 11 by 2 cubed into 5 squared was already 0.055. And that divided by 3 will give you a non-terminating but recurring kind of a representation. Do you see that? This is 0.0183333. Non-terminating but recurring. Why did this happen in this case? Because there was a factor in the denominator. Which was prime factor in the denominator, which was neither 2 nor 5. And eventually, this would be true if numerator and denominator are written in the form that they are co-prime, have no factors other than 1 in common. Yes or no? Right? So this is a broad classification of rational numbers, which is essentially ratio of two integers. And the ratio of two integers could be reduced to a form in which the numerator and denominator have no factor other than 1 in common. That is when we say that their HCF is 1. That is when we say that they are co-prime. Obviously, the denominator is not 0. The denominator, if it becomes 0, then there is an illegal operation in the offing. Division by 0 is an unacceptable mathematical operation. So we don't allow Q to be 0, that is the denominator to be 0. And the two classes of rational numbers, very clear, right? There could be terminating. Terminating would happen. 1, numerator, denominator have no common factor, and the denominator is of the form 2 to the power m into 5 to the power n is of the form 2 to the power m into 5 to the power n. That's when we'll have a terminating. But after having reduced the rational number to the form p by q, where p and q are co-prime, I find that the denominator, in addition to having, or rather, if it has a factor other than 2 or 5 also, if it has a prime factor other than 2 or 5 also, then it would mean that the rational number is non-terminating. Yes, of course, recurring. Non-terminating but recurring, as you can easily. So I hope you have a very clear distinction, a very clear understanding of what it means by the two kinds of rational numbers, right? Now, in both cases, of course, the rational numbers could be written as ratio of two integers. Now, irrational numbers are those that cannot be written in the form p by q, cannot be written as ratio of two integers. Irrational numbers are those that cannot be written as ratio of two integers, and of course they cannot be written as ratio of two integers where p and q are co-prime, q not 0. So those that are not rational are irrational. Irrational numbers therefore would neither belong to the terminating kind. In their decimal representation they will not terminate. They will be non-terminating and also non-recurring. They would be non-terminating and non-recurring, because if they were non-terminating but recurring, they would fall within the purview of rational numbers instead, right? So irrational numbers eventually have a decimal representation in which they do not terminate. The decimal representation does not terminate. Also, the decimal representation does not recur, right? So those are irrational numbers. Now, so we've had a brief stint with rational, irrational in the past and some of their properties. But now just to add a couple of more things to rational and irrational numbers. If p is a prime number, then I claim that for any prime number p, square root of p must be irrational. Square root of p must be irrational. I claim that if p is any prime number, square root of p must be an irrational number. Now the way to prove this is the method of contradiction. The method of contradiction. Let me assume root p to be rational. Let me assume root p to be rational, where p is a prime number. Now, if it is assumed to be rational, then root p could have been written, eventually reduced to a ratio of two integers a and b, could be reduced to a ratio of two integers a and b, where b is not 0. So a and b must be integers. B is not 0, and A and B are co-prime. What do I mean by co-prime? Their HCF is 1. They have no factor other than 1 in common. So if any rational number could be written as ratio of two integers enjoying these properties, right? So if rational, then this is valid, right? Let's keep moving with this. So then this would bring us to A squared is PB squared. Yes or no? A squared is PB squared. Now, see, squaring and multiplying, A squared is PB squared, which means B squared is A squared by P. B squared is A squared by P. Yes or no? Clear? B squared is A squared by P, which means that since B is an integer, B squared would be an integer. Since B is an integer, B squared would be an integer. Right? And therefore, A squared by P must be an integer. Right? Which means P must divide A squared. Right? P must divide A squared must be perfectly divisible by P. The notation for that is P divides A squared. It means P divides A squared. But a property that we looked at in the last session, if P is a prime number and it divides A to power n, where n is any natural number, then P must divide A. Then P must divide A. So if P divides A squared, it really means that P divides A. Yes or no? P divides A? Clear? If P divides A, it boils down to A by P equal to an integer K. It means A by P must be an integer K, yes or no? If P divides A, that means A by P must be an integer K. It means A must be a multiple of P. A must be a multiple of P, right? Now, if A is a multiple of P, plug in A equal to Pk. Plug in A equal to Pk in this equation. In this equation, plug in A equal to Pk. So in this equation, if I plug in A equal to Pk, I end up getting P squared, K squared, A equal to Pk, P squared, K squared is P B squared, right? This would mean P equal to B squared by K. P equal to B squared by K, yes or no? Which also means, can I wipe this portion off? Right? It means K is B squared by P. But K is an integer. So B squared by P will be an integer. It really means that P must divide B squared. If this is an integer, it means P must divide B squared. And if P divides B squared, and if P is a prime, then P must also divide B. So this would mean P divides B. Hey, funny thing, huh? P divides A, which we got earlier. And now we get P divides B. P divides A, we got earlier. And now we get P divides B. That means P divides both A and B. It means P divides both A and B. That means P is a factor common between A and B. That means A and B have a factor P in common. have a factor p in common? Hey, but the original assumption was root p equal to a by b, where a and b have no factors p in common. And what we get is a contradiction to that assumption that a and b have a factor p in common, which means this contradiction really means that our original assumption must have been faulty. Our original assumption that root p is rational must have been incorrect. So root p cannot be rational. Root p must be irrational if p is a prime number. If p is a prime number, root p has to be irrational, right? That's a very important proposition, a very important fact, and you must remember this. So in a very general sense, if p is a prime number, then root p will always be irrational. If p is prime. Right? Bear this in mind. So that's the reason root 2 is irrational, because 2 is prime. Root 3 is irrational because 3 is prime. Root 5 is irrational because 5 is prime. Root 7 will be irrational, 7 is prime. Root 11 will be irrational, 11 is prime, and so on and so forth. Yes or no? Right? So once you understand some of these things, we would be ready for more. Catch you in a short while.